taking modern electrical drive this semester?
Yes, auntie. Why?
Do you mind explain something to me? I don't really understand direct torque control.
Okay, sure, can. Which part you don't understand?
Why don't we start from the top?
Okay, so first of all, direct torque control is being used to drive the induction motor. It was proposed by Takahashi and Noguchi in the middle of 1980s.
Oh, I see.
It offers some advantages over conventional field-oriented control method. It is specialized in high power application. The research on DTC is still significant for improving the performance to obtain high efficiency, reduce torque ripple, and also maximize the torque dynamic.
Oh,
And the research is still significant until now.
Oh, until now?
Yeah, from what I know, the most popular company that market DTC is ABB company.
Wow. Okay.
The first DTC was marketed by ABB in 1996.
Oh. Okay.
Do you want to know what's the advantages using DTC over FOC?
Oh, yeah, sure.
So there are, from what I know, there are 3 advantages by using direct torque controller over field-oriented controller. The first one is it provides simple control structure if compared to FOC structure. And the number 2 is provide robust control due to its less dependency on load parameter variation. And the last one is produce fast dynamic control due to decoupled control structure.
I see. May I know the principle of direct torque control?
That one I'm not really nobody, so you better ask Heng. Khai Zeng. You better ask him about the principle direct torque control in terms of torque and flux.
I see. Okay, thank you so much for your help.
Welcome.
Bye-bye.
Bye.
Hello, Heng.
Hi, morning.
Morning. Shiki told me that you could explain to me the principle of DTC.
Yes.
Can you please explain it to me?
Yeah. First, we have 2 methods to control the machine. First is the FOC and another one is the DTC. And first, FOC we call it a field-oriented control, which is the more complicated control method to control the machine. But by comparing to the DTC direct torque control, direct torque control is a more simple method to control the machine. It is used to control the flux and the torque. Do you understand?
Yeah.
Firstly, you have to know the 6-sector method. And each 6-sector method, we have its own voltage vector to control the flux and the torque.
Sorry, I can't imagine it.
It's okay, let me show you. This is the 6-sector. This is sector 1, sector 2, sector 3, sector 4, sector 5 and sector 6. And each sector with its own voltage vector. This is voltage 1, voltage 2, voltage 3, voltage 4, voltage 5, voltage 6. Can you see now?
Yes, I can see.
This is the 6-sector, and each sector will have its own voltage vector. For example, the sector 1, we have V1 vector and V2 vector. These 2 voltage vectors are used to control the flux. For example, the V1 vector is controlled when the flux is increases, and for the V2 vector is controlled when the flux is decreases. And this is a formula. The change of flux is equal to the voltage vector, stator flux to the respective time. Means that we can control the voltage vector to the flux. Yes. So this is a method how we control the stator flux. This is the reference stator flux, and this is the real stator flux. So we minus it, we will get the error stator flux. Okay. So this is the saturation block. We can set the limit, which means that the upper band and lower band. Okay. Here we have the 3 graphs. So first, this is for the stator flux, and this is for the bandwidth, this is for the switching signal for the inverter. So we can see that when the switching signal is equal to 1, when the flux is increases. And the switching signal is equal to 0 when the flux it decreases. So you can see that it's fulfilled to this requirement. For the flux it increases, the switching signal is equal to 1. For the flux it decreases, the switching signal is equal to 0. Okay.
What about this graph?
Oh, sorry, I forgot to explain about this. So this one, we can set the upper band and lower band for the top error, for the flux error, so that if we reduce the bandwidth, for example, this is the larger bandwidth, right?
Yes.
So if you use the larger bandwidth, the flux will become like this. Like this. So if we reduce the bandwidth, you can get the smooth the flux.
I see. I understand now.
This is the actually this is the principle of the how we control the stator flux for the DTC.
Alright.
Actually, we have another method to control the DTC. To use the DTC to control the torque, which is using 3-level heater DCs. So first, when the torque is increases, we using a switching signal equal to 1. And when the torque it decreases, we use the switching signal equal to 0. And when the torque it decreases critically, we use the switching signal equal to -1. It's okay. This one I will explain later more detail. Okay. So this is the formula involved for calculate the change of torque. And this is the formula. We have the mutual inductance, the inductance value for the stator and rotor. Okay. And this is important. This is the delta stator rotor. Which means that the angle between the stator and the rotor. Okay. So we are using this sector to explain about how the torque can be controlled in this sector. Ayn, do you know which sector we are using now?
We start from here, right? So if that case, it's the 3 sector.
Yeah, good. So I will explain about more detail using this 6 sector. But for example, I will using this sector to explain how the torque is controlled. Actually, this delta is more important. So when we increase the delta, it means that this stator flux will move to this part. So we see to this. So the torque will increases. Okay. If the delta SR is decreases, means that this will move to this part. So means that the stator flux will decreases, and the torque will be decreases. Just now I said I will explain more detail about the DTC for control the torque. Okay, so this is the block diagram how we control the torque. So this one is the reference torque. This one is the real torque. So we add a summing block at here. So we using the reference torque minus the real torque, we get the torque error. Okay, so here we have 3 graphs. For the first is the torque graph, and the second one is the torque error for we have upper band and lower band. For the third graph is the switching signal graph. So first, when the torque is increases, the switching signal is equal to 1. When the real torque decreases, the switching signal will be equal to 0. And the third one, how we can see that the torque decrease critically. Okay, you can refer to the first graph here. The torque is decreased from +3 to -3. So here, +3 to -3. +3 to -3. So you can see that the switching signal is equal to -1. Okay. And another one, how the upper band and lower band to affect the switching signal. So you can see that if we increase the bandwidth, means that the curve will become, the interval will become more wider, so that the switching frequency, we call it switching frequency, will become more longer, the interval. And then you can see that when how we relate these 3 graphs to the previous one, just explained to you for the 6 sector. Okay, so for just now we say that the 6 sector we move to the right and move to the left, right. So when you move to the right, it's about this portion. Move to the left. Sorry, move to the left is this portion. Move to the right is this portion. Means that the torque will decrease critically, and for the left portion, the torque will increase. of that part.
So this is all related to the 6 sector.
Yeah.
This one will go to the left and this one will go to the right.
Right. Yes.
Oh, I see. I understand.
Yes, definitely.
Okay.
Since we know that the switching signal will be affected by the change of torque and the flux. So you can see that this is the torque, this is the flux. So after you go through the saturation block, we will create the switching signal.
Okay.
So all these switching signal we can put in the lookup table, so we can more easily to refer the switching signal for each sector. So you can see that this is the lookup table. So here we have the flux when the flux increases, and this is when the flux is decreases.
Okay.
Okay. So for the torque error status, we have the torque is increased, decrease, and critically decrease when the flux is increases. And this one is when the torque is increased, decrease, and critically decrease when the flux is decreases. So just now I explained to you using the sector 3, right?
Yes.
So I will explain the switching signal in the sector 3.
Okay.
So you can see that this one 0, 1, 0 for the vector 3. So when the flux is increases, right? So we want the torque is increases. So the switching signal for the inverter is 0, 1, 0. And when the flux is increases and we want the torque decreases, the switching signal is 0, 0, 0.
Yes.
And the other is so on. And for the flux is decreases, we want the torque is increases, right? So the switching signal is 0, 1, 1. So all of this is the switching signal to the inverter to control the switch of the inverter. Okay, I can I borrow your book?
Yes, sure.
I want to explain using the 6 sector. So this is the 6 sector. Okay. So when the rotor is rotated to this direction, right?
Yeah.
The torque will either increase or decrease. But when the rotor is rotated to this direction, the torque will become critically decreases.
Oh, I see. Is this how the induction motor is implemented in the hardware?
I'm not familiar to that one. Maybe you can ask Abid. Is more familiar to the hardware of the induction motor.
Oh, Abid?
How to control this.
I see. Okay. Thank you so much, Heng.
Yes, yes.
Bye-bye. Hi, Abid.
Hi. Come and
Thank you. Hey, I just met with Heng and he said that you could show me the setup of direct torque control. Do you mind explaining to me?
Okay, so come. So you need to use MATLAB Simulink first.
I see.
Okay, so you need to this one is for torque hysteresis, and this one is flux torque estimator, and this one is for you put upload to flexi drive. Okay, so we have reference torque and we have flux and torque estimator. Okay, so this one is for D frame and Q frame. Okay, and then we can go to the D space. So this is for control the induction motor. Okay, so you need to click start, and then you have continuous adjustment. As you can see here is negative torque and here is positive torque. So negative torque, the rotation with reverse rotation, and positive with forward rotation. Okay, come and look at here. So this one is FPGA that will control the blanking time. This is for the circuit blanking time. Okay. So this blanking time, and capacitor is to filter the DC supply to make it very smooth. Okay. So this is current controller. So you can control the current at MATLAB. Okay. IGBT is for inverter, as you can see here, and it need a heatsink because IGBT will getting hot when you put a lot of current and more switching. Okay. Current, this one I use oscilloscope. This one is voltage input, and this one for torque reference. Okay. Okay. So we need to use two power supply because this motor need 90 volt to move. Okay, so we connect it in series connector, and then for the third power supply is for load. We use DC motor for load. Okay, so come. So this DC motor is connected with armature resistor in parallel. So armature resistor here got 4 and every resistor is 10 ohm. Okay, we put in parallel and we can get
2.5.
yes, right. Okay, we put it. We can go for demonstration. So firstly, you need to set this DC voltage to 90 volt. Okay. Okay, then you need to continue adjustment to 0 first. Then you click start. Okay, when now I want to show you the step change when it large torque and low torque. Okay, when I click large torque, so when I click large torque, the rotational of the motor will rotate fast, and I click low torque, the rotation will going slowly. Okay, now I continue to step change positive torque and negative torque. Okay. So when I click positive torque, the rotation directly forward, and when I click negative torque, the rotation will at anti-clockwise rotation. Okay, do you understand about this?
Yeah, I think I understand. But I have a question. What is this block selector?
Oh my god, I need to go into class lah. Okay, you may ask Zul for this block selector. Okay.
Okay.
Okay, bye.
Bye. Hi Zul.
Ain.
Do you have some time?
Yeah, sure. Why?
Abid told me that you already done the simulation for induction motor,
Induction motor. For what subject?
model electrical drive.
Oh, modern electrical drive. That subject. Okay, I've done it.
Would you mind explaining to me?
Yes. So, I will show you the result, okay? Okay, we start with the setup first.
I see.
Okay. First of all, this is the setup. I think Abid already explained it to you, right?
Yes.
This is a computer, flexi drive, oscilloscope, motor, and the load. Okay. So this one is the flexi drive. Is he already explained it to you about all the part in the flexi drive?
Not really.
So this is the flexi drive. For this one is a FPGA. This is the blanking circuit. This is the gate driver. This is the current sensor. And this is the capacitor. So as you can see here, there are a screw, right?
Yes.
So this is the inverter. Okay. So the plot selector have 3 parts. The first part is for the D frame and Q frame for the plot 3. The second part is a plot 2 for the current IA, IB and IC. And the third part is a plot 1 for the flux. So plot 1 and plot 3, we can control the hysteresis. Do you know about the flux hysteresis and the torque hysteresis?
Yeah.
Who explained it to you?
Heng Zeng.
Okay, so you already know, right? So I will show you the behavior later. So Ain, I will show you the plot 3 first, which is the D frame and Q frame. When the step change, we can see the torque error there. Okay, so in this video, I will show you. First, I will apply the negative torque, and then I apply a positive torque here. So after that, I apply negative torque back. So I will show you the result. For the first one is the zoom out version, which is when I change from the positive torque to negative torque. You can see here the torque error happened there. Okay, so this is when the negative torque changed to the positive torque. You can see the torque error. For clear view, I will show the zoom version. Okay, this is the zoom version when positive torque changed to the negative torque. Okay, you can see there the torque error become negative value. So when I change from negative torque to the positive torque, the torque error become positive. Okay. As I mentioned before, torque hysteresis band also take part in this experiment. Okay, for the first one, this one and this one, this result, this version of the result show when I using low torque hysteresis band. When I increase the torque hysteresis band, it become this one and this one. Okay, as you can see here, when I increase the torque hysteresis band, you can see the result more clearer, which is the gap become bigger, wider, and clearer for you to analyze. Okay, so in this section I will continue with the plot 2, which is the phase current. Okay, I will show you the video first. Okay, for the first one, I apply the positive torque. Okay, and then I apply the negative torque. Okay, so we see the scope result, which is the oscilloscope result. For the first one is when I apply positive torque. Okay, for the positive torque, the phase of the current we arrange from IA, IB to IC. Okay, when I apply the negative torque, the phase current change to IC, IB, IA. Okay, so you know the arrangement there has been inverse. Okay, then I show you when the step change. Okay, from negative torque to positive torque, the current change from IC, IB, IA to IA, IB, IC. Okay, same with positive torque to negative torque, from IA, IB, IC, change it to IC, IB, IA. Okay, finally I will show you the plot 1, which is for the flux behavior. Okay, as I mentioned before, flux hysteresis band also take part in this experiment. As the motor rotate, it will create flux, right? So we can see the flux inside the oscilloscope. For the first one, I apply high flux hysteresis band. So as you can see here, the behavior of the circle become rough. It show the sharp edges, and from here we can see the vector clearly. Okay, but when I decrease the flux hysteresis band, so we can see the result become like this, which is the circle become smooth, the edges become rounder, and the vector cannot be seen clearly. Okay, so this is happen when we change the flux hysteresis band. Okay, so do you understand about this topic now?
Well, direct torque control is not a tough topic, but once I see the experiment, I could see how direct torque control works.
Good. Okay.
Thank you so much, Zul.
Okay.
Bye-bye.
Bye.
Hey, hi. Hey, what are you doing?
I'm doing some reading.
Oh, about?
Direct torque control for my model electrical drive.
What about it?
Well, I've been asking everyone's help for this topic lately, and I finally understand what is this topic about. Well, this topic is about direct torque control is used to drive induction motor, and then it also have a few advantages of a FOC. And the advantages is especially used in high power application. And not only that, it also have a few advantages such as high efficiency, excellent torque dynamic control, maximum torque capability, reduced torque ripple, improved torque and flux. And not only that, it also offers simple control structure, robust control, and fast dynamic control.
I see you have done some reading.
Yes, and then not only that, by using the flexi drive, it could be seen how the simulation is transferred to the hardware with the help of displays. And finally, I could see how the torque control is used to drive the induction motor and the behavior of the parameter after applying it.
Good for you then.
Yeah. Well, I'm late for my class
Oh.
actually. I'll see you then.
Bye.